Hello, I'm Xuan. Thanks for your interest in our paper, an attention-enhanced multitask model for objective speech assessment in real-world environments. We are the research team from Indiana University, United States. The work was supervised by Professor Donald Williamson. Let's begin. Quality and intelligibility are two different attributes of speech. Quality assesses how well a speaker produces an utterance and refers to the pleasantness of a speech signal. Intelligibility assesses what the speaker said, like the meaning or the content of the spoken words. It measures how well one can recognize what is said in a given speech utterance. Speech quality and intelligibility are key factors when assessing a listening environment, communication channel, or speech enhancement algorithm. Speech can be assessed by using either subjective methods or objective methods. Subjective listening studies are the most accurate forms of assessing speech quality and intelligibility, but this form of assessment is general, costly, and time-consuming to perform when large-scale assessment is needed. Thus, computational objective methods are often used since they provide large-scale assessment in a short period of time. Computational objective metrics can be divided into two categories. Intrusive metrics assess the quality and intelligibility of a distorted speech signal by comparing it to its clean and distorted version. Therefore, a clean reference signal is required. Commonly used intrusive metrics include SDR, Husky, Pascal, E-style. A fundamental limitation of intrusive metrics is the reference signal is usually not available in real-world environments, or it may be difficult to obtain. Non-intrusive metrics, on the other hand, assess speech based on the distorted signal only, which means that real-world assessment is possible. Their assessment generally rely on signal properties and assumptions. Many non-intrusive measures have been proposed in the literature, such as ITU standard P563, ANIC, and SERMA. Although reference-lies-based approaches enable real-world testing, these metrics has been shown to be less correlated to subjective ratings as compared to their reference-based counterparts. Therefore, an active area of research involves developing non-intrusive metrics that can assess speech in real-life scenarios and that are strongly correlated with human assessment. Many data-driven approaches have been developed for speech assessment recently, where the goal is to predict subjective or objective scores. Related work includes Automoise, CNN-based approach, DNA-based approach, QualityNet, NetSQL. They use machine learning or deep learning models to extract features and then build the relationship between the spatial temporal representation of a speech signal and its quality and intelligibility scores. Although neural network-based non-intrusive speech assessment has achieved considerable success, several significant issues remain unsolved and require further development. Like, they perform worse than intrusive measures in terms of correlation to human evaluations. Their predictions are not reliable in some extreme testing conditions, such as very noisy or strong reverberation conditions. The generalization performance in ANSI and realistic conditions are not so good. We also found existing assessment approaches provide singular assessments in terms of quality and intelligibility, but no approach provides both of these assessments. To overcome the shortcomings of current non-intrusive approaches, we propose an attention-enhanced multitask speech assessment model named Armstrong to estimate objective speech quality and intelligibility scores. Our model takes a speech signal as input and generates the corresponding estimates of Pascal, Estoy, Husky, and SDR in a single model. These metrics reliably describe different attributes of speech. The reason why we estimate multiple objective metrics simultaneously is because a unified model that leverages different aspects of speech assessment may be more robust. By applying a multitask learning paradigm in our model, we aim to leverage the useful information contained in multiple related tasks to help improve the generalization performance. Armstrong consists of two components, the shared layers and task-specific layers. The shared layers are constructed using CNN and bidirectional LSTM layers. We use multiple convolutional layers to extract discriminative features and reduce unwanted variations. A bidirectional LSTM layer is then used to further model the global temporal structure. Then every task-specific subnet has its own attention layer and classification-aided module. This allows the network to focus on task-specific information that may improve prediction performance. Attention network is used to adaptively measure the importance of different components within the feature space. From our previous work, we found that jointly predicting the class and true objective score can further reduce estimation outliers, so a classification-aided module is adopted here. For the case task, two training targets are simultaneously predicted. One is the raw objective score of the speech signal, and the other is the corresponding categorical class. The classification label of the case objective score of a given signal S is calculated as follows. We define a capital L and capital H as the minimum and maximum values of the case objective score. Then subscript K is the total number of classes. We train the entire network end-to-end with a unified loss function. The regression loss denoted as capital L regression together with the classification loss, capital L subscript classification of the case task are utilized to update the weights of the shared network. Here, the delta K denotes the task weight of the case objective score prediction task, and capital K is the total number of objective tasks. Lambda subscript K denotes the loss weight of the case auxiliary task, which is a tunable parameter that balances the regression and classification term. The teammate speech corpora is used to evaluate the model performance. Three test conditions are evaluated: the noisy, reverberant environments. We report three established methods for evaluating the performance of non-intrusive methods: the epsilon insensitive root mean square error, mean absolute error, and Pearson correlation coefficient. We compare our approach with several state-of-the-art methods: the auto noise, a CNN-based approach, a DN-based approach, a QualityNet, and NISQA. Our model is training jointly on 4-score prediction tasks, and other comparison approaches will be trained separately on every single task with the same set of hyperparameters. As can be seen from the results in this table, our method outperforms auto-noise, CNN, and DN-based approaches in every score prediction task with a good margin. Compared to QualityNet and NISQA, AMSA still obtains noticeable performance gains. To test the generalization ability of our model in real-world environments, we also consider two real-world datasets, namely conversational speech in noisy environments, Xuan dataset, and voices obscured in complex environmental setting, the voices dataset. Xuan dataset is a set of multi-party conversation recorded in real-world environments with background noise and interfering speakers. The recordings from the closed-talk microphone and the body microphone are used as the clean reference and degraded speech, respectively, when calculating the ground truth objective scores. Voices was recorded by playing clean audio in rooms of different sizes, each having distinct room acoustic profiles. Background noise was played concurrently. Therefore, voices cover realistic, noisy, reverberant conditions. The foreground speech will be applied as clean speech, and the audio recorded by various of microphones are used as degraded speech. We assess 1,500 distorted signals from each of the above corpora and compare AMSA with the best two comparison approaches, the QualityNet and NISQA. We summarize the results of this experience here. Not surprisingly, the performance of AMSA is declined compared to the results on the simulated timid datasets, but its drop is much smaller than that of QualityNet and NISQA. When considering these challenging test conditions, where the speech corpora and distortions are totally unseen, the results are promising. Let me summarize our work. In this paper, we propose an intention-enhanced multitask model for speech assessment, aiming to use a single model to predict a number of objective speech quality and intelligibility metrics simultaneously. In particular, applying multitask learning improves feature learning due to the underlying commonality among tasks. Different from existing non-intrusive approaches, we incorporate a self-intention layer to detect the patterns within each feature map and that's relevant to the current prediction. This operation significantly reduces the estimation error and improves the generalization ability in real-world acoustic environments. We also conclude that jointly training a classification-aided regression model is promising for speech assessment. This is the references for the slide. Okay, thanks for your attention to our paper. For more information, please refer to our paper and website. Thank you.